All right. As you notice that we are slowly moving more into more networking issues. Kerberos itself was networking, because before Kerberos we were talking about all this encryption and cryptography, which didn't really require networking. You could just do it on a single node. But Kerberos is one thing that we talked about that required an organization and a network and so on and so forth. Now transport layer security is exactly the same thing, is that now on the internet. And many of you have heard about SSL, so we'll talk about that most of the time and then tell how it is related to TLS and HTTPS. And then toward the end we talk briefly about SSH. So if you want to secure applications, you have choices of many layers. You could secure the IP layer, and we will talk about that. That is called IPsec. Or you could secure the TCP layer, and that is what we are going to talk today, and that is called TLS, transport level security. And or you could secure the application, which is done in SMTP by using S-MIME. Basically in SMTP, which is the mail protocol, you could encrypt the content and then send over. Alright, so that is called S-MIME. So the advantage of doing at IPsec layer is that all protocols, all transport protocols are covered and all applications are covered. Alright. The advantage of doing at TCP again is similar, is that all application protocols are covered. And the advantage of doing in the application is that basically this is not an advantage, but basically is that you can design it very specific to a protocol or an application, although it doesn't cover any other application. All right. So in some sense lower is better. However, there are several problems with IPsec, that you see more application of TLS and SSL in the internet than IPsec. All right. So every time you do HTTPS, you are doing SSL or TLS. All right, and that you do every day. So, and we will use them interchangeably almost, because as we will see the next slide, TLS is simply an update of SSL. What they provide is four things. First, they provide the facility to crypto negotiate what encryption scheme we will use, what hash methods we will use, so you can negotiate the one side and the other side. By the way, this is transport, so there are only two sides, so there is no negotiation within the network. It's just end-to-end, receiver and the sender. Key exchange, so then you can exchange your secret key. Once you know what algorithm you are using, then you can use that, and that is done using public key certificates. Then privacy, obviously you do encryption. Once you have the key, you can use encryption. And integrity, once you have the hash, you can ensure that the message is not changed by anybody on the way. All right. So these are the four things that the SSL provides: crypto negotiation, key exchange, and then privacy and integrity. So the history is that SSL was developed by Netscape. As you know, Netscape was the first company to put out a browser back in 1994. When the browsers came out, people said, well, we can't use it because there is no security. So they invented a method. Actually, they just used the technology available at that time. So they invented a method, failed twice. SSL version 1 was so bad it was never deployed. Version 2 had major issues. So version 3 developed very quickly. And version 3 is what is being used quite a bit. And then when version 3 became deployed, then IETF took it over and made a standard based upon version 3, and that standard is called TLS. Now, the changes are, so the TLS is actually, when you send messages, TLS is encoded as version 3.1. When somebody negotiate SSL version 3.1, they are negotiating TLS version 1.0. Okay, so it's to that level. So the differences are small, but the protocols do not interoperate. So you cannot have one side speaking SSL version 3 and the other side is speaking version 3.1, even though they are just 0.1 version apart. All right. So if either both sides speak 3 or both sides speak 3.1. And obviously nobody wants to speak version 2 because version 2 is known to be, have a problem. So we don't speak version 2. And so version 1.1, so after this version 1 was done, TLS version 1 in 1999, version 1.1, which is encoded as SSL version 3.2, was done in 2006. And that added a protection against CBC attacks. So there were some CBC attacks that were discovered in the meantime, so that was protected here. And then there is a TLS version 1.2. Yeah, in the next slide. TLS version 1.2, which is encoded as SSL version 3.3, that was added in 2008. Let me see if I missed anything in the previous. Yeah, so this previously is done. Yeah. So TLS version 1.2 was done in 2008, and it added many of these things. It replaced MD5 SHA-1 with SHA-256. It replaced MD5 SHA-1 for the hash with SHA-256. It replaced MD5 SHA-1 from the signature in the signature field with SHA-1. So MD5 was removed basically in summary. And it enhanced the clients and the servers specification for hash and signature algorithms. So some new algorithms were added for hash and signatures. And it added authenticated encryption ciphers. So basically, authenticated encryption means that you have encryption along with message authentication, right? So that was added. And then extensions definition. So basically they allowed some more extensions, and so they just defined a way to define extensions. So people can add extensions, and then they added AES. Anyway, this was 2008, and now after that 2008, so we are almost very close to right now. They have another RFC which did not generate a new version of TLS. It's still called TLS version 1.2, but they added a requirement that you will never use version 2, SSL version 2. Previously there was not a requirement, and some versions accepted it, or some implementations accepted it. Now if you are doing 1.2, you will not accept version 2. All right. So summary of this is that SSL and TLS, they are one basically extension of the other, update of the other, and they are just coded in the same kind of messages. Only the version number for TLS 1.0 is SSL version. What is the version for 1.0? SSL is 3.1, and for 1.1, 3.2. For 1.2, it is 3.3. So they are going up by 0.1 every time they go up 0.1 here, and the messages are still the same. So when looking at a message, the only way you can tell the difference between SSL and TLS is if it is 3 or below, then it is SSL. If it is above 3, then it is TLS. All right. So SSL itself consists of 4 protocols, and they are organized as follows. There is one thing called Handshake protocol. Second is the Cipher Spec. Third is Alert. They are all they all run on the top of record protocol. All right, all of them run on the record protocol. So we will actually go in this order. Book actually goes in the bottom up. I am going to go top down. So basically we will talk about these protocols. So what the handshake does is, handshake negotiates what algorithm we are going to use, period. What is the crypto, what is the hash, and so on and so forth. In fact, you might even get the key with handshake. With Cipher Spec, change Cipher Spec is very simple protocol. It simply says, okay, all right, let's begin. That's the only command which says that, okay, so we negotiated the key, now let's begin using that key. So that is one spec. And then alert protocol tells you any errors that might happen. It's like ICMP for IP. All right, all the error messages are sent using alert protocol. And record protocol is what is the basic main protocol which provides the encryption and the authentication. All right, so this uses the keys that were generated using handshake, and so everybody has all of these messages are encrypted using the record protocol once the keys are done, right? So and HTTP is shown here because HTTP would be an application that will use SSL, so it uses like this. Basically all of these things are done and SSL record protocol is ready to go, and then HTTP will send messages which are encrypted and authenticated. So handshake allows the server and the client to authenticate each other, to negotiate encryption and MAC algorithms, to negotiate the keys. And so there are several messages which are coming up in the next slide. There are several messages which establish the capabilities, 4 phases actually. First, we talk to each other and say, well, what is it that you can do, what is it that I can do, right? So a little iPhone or some other smartphone may say, well, I cannot do AES, I can only do 256-bit this and that, right? So that is done in the first phase. Then they do the authentication, server authentication and the key exchange. So server is authenticated first, that I am talking to the right bank, that I am talking to the right company, and then you get the key. And then the client is authenticated next, and the key is exchanged, and then finish. So here are the messages in 4 phases. This is phase 1, the first dotted line. Up to the first dotted line is phase 1. Then this is phase 2, this is phase 3, and this is phase 4. Alright, phase 1 is simple. Phase 1 is simply establish the capabilities. Is that client says, and notice that it all goes in clear. It says, look, I am so and so, and I can use these protocols, these ciphers. My version is so and so. So basically, it will say that I am going to use version 3.1 or 3.2, whatever version, and that I am going to use this encryption scheme, this compression scheme, and here is my random number. Okay, and the server then selects from these choices. So if the client says I can do only SSL version 2, then the server has to either select that version 2 or reject it. Right? If the client says I can do version 3.2, server can say, well, I can do only 3.1, so I will take 3.1. Alright? So the client specifies the highest it can do, and the server takes the highest that it can accept. Right? So that response comes back. So it says, hello, here is the cryptographic algorithm I have selected, here is the compression algorithm I have selected, and here is my random number. All of this is done in clear. Now it is not very protected because somebody could change along the way, and this has been done. Because if suppose this guy says I can talk SSL version 3.2, somebody in the middle can change it to version 2, and then version 2 will be negotiated, and then that person will be able to break it. So that's why they have, actually there are two protections for this. It will come up in the end here, but there are two protections for this. First of all, this is SSL version 2 will not be allowed, and second is that they check out that even though these messages were not encrypted, they were not changed. That will come up in a minute. All right, so once we have agreed on the encryption, then this is the optional part where server is authenticated. If server is authenticated, then the server sends its certificate, it sends a key, and it sends a certificate request. Actually, certificate request is misnomer. I find it confusing. When somebody says certificate request, it looks like I'm asking, please send me your certificate. That's not what it is. It is the CA. It is basically a message in which I tell you, which I send this, the CA's name, the certificate, his certificate, and here is who the certificate is from. Kind of confusing, but anyway. So that is all certificate, and then finished. Hello, done. So these messages are sent one way. Now once you have this whatever has been done from here, the client will send its certificate, which will be encrypted with its, doesn't make sense, does it? Yeah, I have to check that. Why is it encrypted with them? So this one says this is encrypted with the client's private key. The question is that the public key is right here inside. So I have a little problem as to why it is encrypted when the public key is there. So how would they decrypt it? But anyway, we can check that out from the book. Okay. All right. So the book actually doesn't talk about this at all. So I may have made a mistake. Certificate verify. Okay, this might be my mistake. The book doesn't say anything about that message. For the time being, I'm going to remove that encryption, and we can double check later on. Alright, so the client sends a certificate, and based upon the random numbers, it generates what we call PMS, pre-master secret. So that is the first step in generating the master secret, and master secret is the master key. But before we generate that, we generate PMS, and that one is encrypted with the server's public key. That makes sense, right? We know the server's public key, and we send the PMS there. Based upon that PMS, both sides can compute the same master key. So both sides can compute the master key. So this one has computed, this one has computed. The master key is not exchanged, but they have computed it, right? And then this says certificate verify. Basically, that it's all done. The end of this page. Then there is change cipher spec. So this is actually phase 4. And this is the message which actually belongs to the other protocol. This is one byte message, says that now let us use that key to communicate. And then this side will send hash and MAC of all previous messages. So this will send hash and MAC. So it will combine all of these messages and hash them and get the message authentication code and send it. So if any of these messages were changed by anybody, now this is encrypted here, right? This will be detected here, and this one will do the same thing. It will say, okay, let's go with the new key, and here is my hash. So this one will also send hash and MAC of all the previous messages onto this side. So this can verify that the other side also got the same messages. All right. So that's the trick, is that you can communicate in public openly without encryption. However, you can still protect that by having this kind of MAC later on, message authentication code later on. Right. That is one thing. And the second, basically, let's see. And everything else is standard actually. So most of the other protocols, that even SSH and other things, they do exactly the same thing. They negotiate first. Once they have negotiated, then they generate the key, and and I don't know whether SSH is after SSL, but now the later ones will do this as well. Okay? Yeah.
So what would they do if they found they've been compromised at the messages?
Then basically they will disconnect and restart, maybe try 3-4 times and then give up. That's where the alert protocol comes in. The alert protocol will come in a minute, but basically that's where the error message will be sent, the connection will be reset. If something has been changed, then obviously you are not going to do any more. You have to start from the beginning. Hello. Because the hello message might have been changed, the very first message. Alright, so all the messages for the handshake are TLV included, TLV encoded, and all of you know what is TLV, type, length and value. So there might be 1 byte of type, 1 byte of length, and then whatever is the length, that many value fields, right? So types are, these are the messages 1, 2, 14, 12, 16, 13, and so this basically covers all of these messages here, plus some that we didn't probably show. So that includes client hello, server hello done, client exchange, server key exchange, certificate request, certificate. See, the thing is, certificate request means CA name. Alright, I think this probably means that these are the CA names I understand. So if when you supply the certificate, supply me from one of these people. I think that would be a big list though, I don't know. And then the certificate sent by the server, and certificate verify the signature of the hash of the messages, and handshake finished is okay. So that's another point here. What they do is for the for taking the hash, they divide the messages into two halves. Actually, let's say they divide into 32 bits and 32 bits, first into blocks, and then they divide each block into two halves. The left half is done by MD5, and the right half they do it by SHA-1, and then they exclude both of them, and then they send it over. Okay, and I think previously they were not exclusioring, they were just going to send both of them, and then they realized that that is weaker. So really the stronger thing is to combine both of them into one and then send. So that way it turns out that if you break only one algorithm, suppose you break MD5, right, your messages are still protected because the SHA will not match. Alright, if you break SHA, the MD5 will not match. So they thought by using two algorithms they are getting the strength of 2, but if you keep them separate, then you're really not getting the strength because you know half will be broken and this half will not be detected by SHA. So then they have to now exclusive OR. So if either half is broken, then the whole thing doesn't work. All right, now little bit more detail about the first phase, the capability negotiation. So these are the methods which are supported, these are the encryptions which are supported. So for the key exchange, now remember the key exchange method was Diffie-Hellman. We talked about Diffie-Hellman is that you send some numbers to me and I send power of those numbers back, and then we can figure out what the common secret is. So that is the method which is generally used. You could also use RSA. Now Diffie-Hellman has three methods. Three different variations of Diffie-Hellman they use. First is called fixed Diffie-Hellman, second is called ephemeral Diffie-Hellman, and third is called anonymous Diffie-Hellman. So fixed one is the standard one that we have talked about, where you use the public keys and send the generator and your random number and so on and so forth. And so that is the standard one. But ephemeral means temporary. One time secret key is generated after the certificate exchange and authentication. So this one basically does not use the fixed public keys. So after you do the certificate exchange and authentication, then you generate a secret key, and that is used just one time. So this is why it is called one time Diffie-Hellman or temporary Diffie-Hellman or ephemeral Diffie-Hellman. Then the third one is anonymous Diffie-Hellman. In this case there is no authentication done, only public key exchange done. Since there is no authentication, this is subject to man in the middle attack, right? MITM, man in the middle attack. And because there is no authentication, anybody else can play in between. But there are some certain circumstances where you don't need the authentication, or or you cannot do the authentication, so you just use that. So obviously this is the weakest, this is the second, and this is the strongest one among these three. And then there is Forteza, which is basically using hardware, using PC cards. So if you want to negotiate with PC cards, then that is the name of it. So that is the key exchange method. Cipher, the encryption methods which are supported are RC4, RC2, DES3, DES40, IDEA, and Forteza. By the way, DES40 means 40-bit keys, and DES uses 56-bit keys, right? So why 40-bit keys? Well, there was a period when the United States prevented any company from selling any encryption cryptography equipment to any other country if it was stronger than 40-bit. Alright, so during that period, inside the country we will all use 56-bit or 112 bits or whatever encryption, but if it goes across the US boundary, it has to be 40-bit. And I remember in those days, every company discovered a way to get around it. Every US company had a branch in Ireland or some other place, and they can sell it, but US cannot sell it. Right? So finally US realized that this is not very effective, so nowadays they don't enforce that law. I don't know whether the law has been removed or is still on books, but now people can exchange. And in fact, in between there was a period when people complained, the banks complained, they said, look, we cannot do financial transactions with 40-bit keys. There is a lot of danger. So they said, okay, all right, we will give an exception for financial transactions. So there was a period when 40-bit, and then there was a period for exception, and now there is a period where there is no rule basically. So that's why many of these things had 40 bits in between, so that's 40. Alright, MAC algorithm. So MAC is MD5 or SHA, Cipher, stream or block, is exportable, true or false. So these are all the fields that you have to fill in along with. So you select one of these and then you specify. So the thing is that if you specify RC4, clearly it is a stream, clearly. Now the question is whether it is exportable or not, maybe true or false depending upon the size of the key. Right? Here exportable has to do with the United States. And the hash size, key material used to generate the key, and then the IV size of the IV for CBC. So all of these fields are there in those messages, and if you want to know more about these are the URLs from Wikipedia. So master secret creation. We first, a 40-byte value based upon the nonces is created, 48 bytes, which is long, 48 times 8 bit, 384 bits. And so that is the master secret. And how it is generated? It is generated using first a pre-master secret, which is exchanged using either RSA or Diffie-Hellman, and then you hash it. How you hash it? You take the MD5 of the pre-master and you take the SHA of the letter A. All right, and then you do the pre-master secret again, and then you take the random number selected by the client, and then you take the random number selected by the server, and there are a few more fields. Actually, it is given in the book, it's a little bit longer. You take all of that and you do MD5, that gives you master secret. And there are a few more letters actually like this. Why letter A, I have no idea, but basically they have letter A, and then the next one is letter BB, and then letter CC. So they just generate some random numbers, random looking numbers, because SHA of A is probably not, once it's computed it is not random. So you calculate all that and you get the master secret from pre-master secret. And and then the cryptographic parameters are client write MAC secret. So this is one parameter. Its name is client write MAC secret. So this is the key that the client will use to encrypt. Oh, sorry, client write MAC. This is the key that the client will use to compute MAC. Okay, client write. I don't know how they selected this kind of word, but anyway, client's MAC key. That's all there is. Then a server write MAC secret, that is the server's MAC key. A client write key, so that is the client's encryption key. Server write key, server's encryption key. Client write IV, which is initialization vector, and a server write initialization vector. And all of these, or many of these, are generated by hashing the master secret. So master secret is generated by hashing the pre-master secret, and then by hashing this, and there is the whole formula for that, you can get all of these different secrets, different keys. So all of these keys are generated from the master key. All right, so that finishes the first protocol among the 4 that we talked about. Again, going back, SSL has 4 protocols. The first part is the handshake protocol. So we talked about that so far as to what the message fields are, what are the different different cipher specs, etc. allowed. Now we go to the next one, which is the chain cipher, which is actually pretty simple compared to what we have gone through in this one. It's just 1 byte message which has a particular byte pattern which says here. Let's start those values that we computed. Chain cipher spec protocol. It's a single 1 byte message and causes negotiated parameters to become current. Hence, I think this could have been just part of the handshake. All right. The reason they did not make it part of the handshake is because handshake is done once, change spec is done many, many times. So after every few minutes, we might change the specs, and so we might negotiate a new key. So we don't do the complete new handshake because we already have a master secret. We just have to generate the keys, right? So that's why they kept it separate protocol, gave it a separate protocol. But this is basically saying that let's use this secret, let's use the keys that we just computed. Alert protocol is again simple. Basically, it has 2 bytes. First byte says what is the level, and the second, what is the level? The level could be either warning or fatal. All right. Fatal means stop right away, immediate termination. Warning is be careful. But we continue. So that is 2 levels of level, and then the alert. Alert could be one of these numbers. 0 means close, 10 means unexpected message, 20 means bad record, and so on and so forth. And the list continues. Each of these type is either fatal or warning, and either SSL or TLS or both. So this one was used only in SSL version 3, this one is used only in TLS, and so on. So TLS in particular has much longer list of alerts than SSL version 3. Certificate revoked, certificate expired, unsupported certificate. So you get this kind of message, and then it could be warning or fatal depending upon what the user wants to do. So generally you see these warnings flashed on your screen, and the user generally says continue, or could say stop. So that is the alert protocol. Finally, the record protocol, which is the bottom of the all 4 protocols, as we saw here, the record protocol. This is the encryption and decryption. So this is also straightforward. Basically, you use whatever algorithm you selected, and the main thing to know is that the message is compressed before encryption. In HTTP, there is a lot of redundancy, right? And therefore, message is compressed, and before encryption, that reduces the number of bits, and then the integrity is done with whatever we selected, HMAC, similar to HMAC but different padding. So that is what is described next. Basically, you take the application data, break into blocks, each block is compressed, and then the MAC is added to each block, and then it is encrypted, and then we add the headers and we send it off. Alright. So notice that the MAC is encrypted inside this. This is basically MAC then encrypt. And so the only new thing here is the compress. All exchanges are in record. Now this is for the record protocol. The records can be as long as 2 raised to 14 or 2 raised to 16 minus 1 bytes. Standard allows multiple messages in one record or multiple records. So you could put, it's basically what it says is that this is many to many relationship. You could have many messages in one record or one message in many records. Right? Most implementations use one message per record. So although this is allowed, implementation just you take every message that comes from HTTP or from SSL for that matter and put that into one record. There are 4 record types: chain, cipher, spec, alert, handshake, and application data. So basically the record protocol looks like this. You have a record type followed by version number followed by the record length. That is just the header, and inside this there will be messages. Each message will have a message type, message length, and the message. Alright, so each record can have many messages or could have part of a message. So the record could belong to one of these protocols. It could belong to the chain cipher protocol, could belong to alert protocol. If it belongs to chain cipher protocol, then it is just 1 byte, 20, and that's it. There is no version number, there is no record length. If it is alert, then it will have the record type of 21 and then 2 bytes. If it is handshake, then we talked about that earlier, and so on and so forth. So that finishes SSL, and let's just summarize one more time, and this is the key, that SSL runs on the top of TCP, now not UDP, TCP. Okay, and then it has 4 pieces of protocol, sub protocols: handshake, cipher change, alert, and the encryption protocol, and everything from these 4 goes through that protocol, and therefore it is encrypted, except obviously some of the handshake messages will go through clear. Any question about SSL? Basically, this will continue on many of the next few chapters, because what we have done is we have already talked about AES and DES and so on and so forth. So they just have to select the right hash function, right encryption algorithm, and then basically use it. So this is what this is about, and same thing with SSH and other things. Okay. So with TLS, as I said before, TLS is just an extension to SSL with minor differences. In the version number, obviously has been changed from 3 to 3.1, and they uses HMAC, which is the keyed MAC, and they use a pseudo random function that expands the secret based upon HMAC during SHA-1 and MD5. So the secrets, we saw how they expand, right? They take lots of things, they concatenate them together, and then they do MD5. We saw their MD5, but could have been SHA-1 as well. Has additional alert codes, has some changes in the supported cipher, so there are some more algorithms, more encryption algorithms are supported, and certificate types and negotiations are done, more certificate types, and changes in the crypto computation and padding. So we didn't go into the padding details here. Somehow we didn't go into the padding details, but that is different in TLS. All right. So TLS and SSL are same and almost same, but with some extensions. All right. And then we come to HTTPS, which is, again, we have already talked about everything that we need to talk about, because HTTPS is nothing but HTTP over SSL. And that means that you basically do whatever we talked about. And the main change is that now you use the port number 443 rather than 80. So with port 443, it goes through SSL. With 80, it goes straight to HTTP module. And with HTTPS, the URL, the document contents, the form data, cookies, HTTP, everything is encrypted. All right. Anyway, so the summary is, every time you see HTTPS, you are doing SSL or TLS. So before you do HTTP request, you do TLS handshake, and before you close the, so basically you have to somehow enclose that, in the sense that you first open the TLS and then open the HTTP, you first close the HTTP and then close the TLS, things like that. And then the question is, how do you close the TCP connection? TCP connection has to be closed after the SSL has been closed, right? Everything has been closed, then you close TCP. Now, having said that, it is quite possible that the TCP may have to be closed abnormally. For something happens and the TCP connection cannot reach, something like that, right? So that case is handled. Must handle abnormal TCP close before alert exchange is sent or completed. Remember, one of the alert was close. And so that simply says that, look, I want to close the connection now, right? And which is a normal thing. It's actually not really a alert, but and that is just a normal thing, right? So so normally you close that connection and then you close the TCP connection. But if the TCP somehow closes before, that is also okay. Then basically we'll just close the SSL connection. Any question? Yeah.
Is like SFTP, is that the same thing as like HTTPS?
SFTP?
Yeah. Or is that
Okay, that's slightly different. So that would be FTP over SSL, right? Now FTP does two connections, control and data, right? And I am not sure, I mean, I have to read myself, find out whether it is required that you encrypt both, or you encrypt one, just the control part, and leave the data alone, or things like that. Here that is not a choice. Here in HTTP, the control and data are intermixed. There is only one connection, right? So that might be a detail that we need to look it up if you want to do SFTP. All right, then there is secure cell. Oh, before I give you secure cell, I need to give you an update. Please pass this backwards. So SSH, all of you have used SSH, I suppose. SSH is just a secure telnet, right? Remote terminal protected one. So SSH1, and now there is SSH version 2, which is what we use, and it is documented in these RFCs, and these are widely available, and we have all used it. So with that introduction, let's go through the protocols. And SSH has 3 protocols. So they don't have changed Cipher Spec. but they have three protocols. They have authentication. First, okay, so they have authentication, they have connection, and they have encryption. So this encryption thing is called transport layer protocol. And by the way, SSH is also a transport layer security. I mean, it is not called TLS, but it is also transport level security protocol, right? I mean, TLS just stole the whole category name as one, but this is in the same category, transport level, because it works on top of TCP and it provides security. And just like TLS, it has two layers actually. The one layer which does the encryption and integrity, and but the keys etc. you have to exchange, you have to negotiate, and those are done by these two protocols. So the numbers here 1, 2, 3 means in the order that we will discuss them. So number 1 we will discuss. In this case, somehow I decided to just follow the book's order, which is the transport layer first. So if you know the keys etc., then all you have to do is set up the TCP connection, and then you have to specify what is the protocol version and software version, and this one specifies what the protocol version and software version. Then you negotiate the keys. Then once you have the keys, then you can start the this encryption, and the encryption proceeds as follows. You take the payload, compress it. After compression, you add the packet length and the padding length and add the padding, and you add a sequence number. Alright, and the interesting thing is that the sequence number is added and MAC'd, in the sense that when you calculate the MAC, the sequence number has to be added, but it is not sent. So it is not encrypted. Only thing you encrypt is packet length, padding etc. etc. You encrypt that much and you add the MAC, and the MAC is outside the encryption. So it is encrypt and MAC. Alright, and then you send this. At the other side, you have to do the same thing. You have to generate the sequence number, and if some messages are missing, obviously the sequence number will not match. Put the sequence number, check the MAC out, and check the encryption out. Okay. So the second thing is the authentication protocol, which consists of, very similar to the TLS, is that you actually it's slightly different though, but basically the client says to the server, I want to authenticate, but I don't know what method to use. And so the server says, you are not authenticated, but I can accept the public key or password. It gives options of two methods. Then the client says, okay, here is my password, and I am selecting the method of password. And then the server says, okay, success. So there are three messages in this protocol: request, failure, and success. And again, this is kind of strange as to how this came about. Is that first you send method equal to none. They could have sent that, okay, I can do password, and just like we do in TLS, they could have said that I can do password, and then the server and certificate, and server would select one of those, right? Here the server specifies and the client selects. And by the way, this is user authentication. So what about the server authentication? So the server authentication is fixed. Server authentication is always by its certificate. And what you do is when you do SSH, very first time when you go to a server, you get their public key. Now, whether you want to trust that public key or not is up to you. So it will ask you, the user, it will ask you the user on the screen. So the key is this and that. Do you want to store it? And you say yes. I mean, what else will you say? Once it is stored, that becomes the permanent key. Then anytime you connect to that server, basically that's the public key. Right? So you keep a list of public keys, and in that list is this server key added, basically manually. And many of these decisions were like this because this protocol SSH was done by somebody on his own time, and he just started using it for himself or something like that, and then suddenly people found out and they said, oh, we like it, let's do it, So the whole history behind it. But anyway, so the server authentication is done by this key, which is the user just has to verify and accept, and then the client has to be authenticated every time, and so the client has to supply the password generally every time. Or it could supply a public key too. I mean, it could generate. So these are not really the certificates as such. These are not certificates supplied by VeriSign and other people. You could just generate in your computer a private key and public key pair, and send the public key. And again, the question is, how will they really verify? Because there's no root, so things like that. So that weakness exists. But basically, you can use just the password and authenticate yourself. Then you have to set up channels. So the way SSH works is that once you have set up this master connection, master pipe or whatever you want to call it, you can put many little channels inside it. And you can use it for different purposes. So there is a connection layer which allows you to do that. So it is used for multiple logical channels, and any site can open a channel. So this site can say I want to open a channel number 2, and this site will say I want to open channel number 3. And for each channel, basically you open it, use it, and close it. Open, use, and close it. And there are 4 types of channels. One is for terminal sessions, the normal one, X11 session, which is the Windows session, and then forwarded TCP/IP and direct TCP/IP. That is for any other applications other than these 2. You could use SSH for any other application by forwarding their ports. And there are 2 ways of forwarding the port. One is called remote port forwarding, other one is called local port forwarding. The SSH name for remote port forwarding is forwarded TCP/IP, and then this is direct TCP/IP. And actually next slide explains this. But basically there are 4 types of channels that you can set up, and you can connect and disconnect, and so basically keep different channels separate inside a SSH connection. So by the way, if you do SSH, you can transfer files while inside the SSH sessions, right? So that is the kind of thing where you can use a channel. Now, port forwarding is not from the book, by the way. It was so confusing. It took me to read lots of other sources to figure out what exactly is happening in the port forwarding. So I prepared this slide one time, and then I re-prepared it again last night. That's why I gave you the revised handout. All right, so listen carefully this one. Basically, what port forwarding allows you to do is that once you have set up the SSH tunnel, then you can use any application which is not secure over this tunnel. So that will be secured. Any insecure application can be used over SSH tunnel. And there are 2 ways of forward. So basically, one way of forwarding is that, let's say you are doing mail service. You want to read your mail at the work when you are at home. Host H is home, host W is work. So you SSH to work. SSH to work, and then you can do terminal. Anything you can do on the terminal, you can do in the SSH window, right? But let's say you want to read the mail and you want to read encrypted mail. I mean, you want to encrypt it so that anybody outside of your company or on the way cannot read it. So then what you do is you forward the port. Basically what you do is you tell the other side that, look, everything that I send on this channel that I am setting up, new channel, please send it to the host S in the company on port Y. That is where my server is for the application. Host S Y, that is written as S:Y. S is the IP address, Y is the port number. And you tell the application on this side that your server is located on host H at port host H at port A. Host H at port A. So instead of this one, when it generates a message, instead of sending it to SY, it sends it to HA. Alright, and obviously SSH is listening on that port. SSH is listening like any other server can listen on any TCP port. SSH is listening on A. So whenever application sends it, SSH gets that message locally by a local loopback. It goes to TCP and it comes back to SSH. Then it puts it into this logical channel. It goes there. There it is decrypted and then sent to host S on port Y. And so now the host S doesn't really know that this message was encrypted along the way or that it came by SSH. All it knows is that it came from application here. Basically it would have, if they would have connected directly, they would have just gotten the same set of messages, right? But those messages would have been in clear. Now these messages are all encrypted on the internet. All right. So now you have to understand the two things here. First of all, first is the port numbers. So the X is the port number for this application that it is sending. This is the source port number. A is the destination port number. Right? Here B is the source port number, C is the destination port number, which is generally 22. For SSH, the destination port number is, for SSH server, the standard port number is 22. Right? C is 22. D could be any number and Y is whatever this application is listening on. So if it is FTP server, it is listening on port 21. Right? If it is a mail server, it is listening on some port number, right? So those Y is standard and C is standard, but everything else can be any number here. And the arrows are not really meaningful, because all TCP connections are bidirectional, right? But the arrows simply show the direction of the connection request, TCP connection. So this application starts request a TCP that I want to set up a connection with port A. Right? So that is why the arrow is shown like this. And here this SSH requests the TCP that I want to set up a connection with host S on port Y. Okay, so the arrows are simply for the connect request. And very often the application doesn't really rely on some other host. It could be right on the same host as the SSH. If that is the case, then you don't say SY, you say 127.0.0.1Y, because 127.0.0.1 is localhost. All right. So oftentimes if you have used SSH, this is the kind of command you give. You say, I want to SSH to host W, but I want to do the local port forwarding such that my port A is forwarded to host, generally you will write localhost here, :Y port, that port. All right, the word LOCALHOST is put there instead of S. All right, and the word L means I am going to do start from this side, from the local side. The other alternative is that somehow your company does not allow you to SSH from outside, your firewall prevents you, then you can start the SSH from there, from the company, and come home. All right. In that case, the SSH connection goes like that. However, you also say that basically I am going to do the port forwarding here. You tell the home computer that I will forward your A port to the Y port here. So that is called remote forwarding. So the main difference between local and remote is very subtle, very different, is that in the local forwarding the client starts the SSH, and then the client tells the server, the other side, that please forward the traffic to Y. Right? In the remote forwarding, okay, now here you think host W is the client, by the way. Okay, so don't get confused. This is the client and this is the server. Right? The client SSH starts the tunnel, which is host W, and informs the server SSH, which is host H, that I will forward the traffic on this channel to Y. I will forward the traffic. So this is I will and please forward. That's the kind of thing. Local means please do it, and this one says, starting point says, well, I will do it. All right. So if that is the case, that is the remote forwarding. And if you want to read all of this clearly, then this is described in this book, which somehow is online. I don't know why it is online, but the whole book is online. SSH for Dummies or something like that. The name of the book is. Okay. So anyway, so this is about port forwarding. As I said, in the book it is very, very vague. So please, if you have any confusion, any question not clear as to what's happening, ask right now. Yeah.
So left R is local and remote, not left, right?
Left R. Where is R?
Left A. Yeah, the uppercase L.
Left A is this one.
L means local.
Yeah, L means local forwarding, R means remote forwarding. So when you start the SSH command, this is the SSH command you will do. This is the command you will run here on host H. This is the command you will run here on host W. Right? And I should probably label clearly so that you know that this is a client and this is a server, this is a server and this is a client. Right? Because people will normally think that this is always the server. So this is not the server, this is the client, this is the server, and that is shown by this arrow. The client always starts the connection to the server. And if in this example S is same as W, then this will be localhost. So you are on this host and you are going to say SSH minus RA colon localhost colon Y, and then space H. H is the destination. Yeah.
So you do a remote forwarding, and maybe you were going out of town and wanted your work email to be forwarded to home.
Exactly. So the thing is, when your firewall doesn't allow you to do this way, you just start from the inside out, and then you're going out of town or going to be home, and then you can connect it that way. Well, going out of town is kind of difficult, looks to me, because When you set up the tunnel, this host has to be up. And if you want to be in Germany and your host is not there in Germany, you can't really do from work, right? But for home you can do, because your home computer is up, it has a server running, it can accept the SSH connection, right? If you had a connection in Germany where your computer is already there, then probably this will work. But if you are going to take your laptop, it will not work. A laptop is not there to accept the connection. So this SSH tunnel is set up before you reach home, and then when you reach home, then you can basically start reading the emails or whatever you want to read. Yeah.
The SSH channel is set up, and then just the application or the TCP layer decide to use this channel.
Now, the application doesn't know anything. So this is the interesting thing about SSH. That only thing application has been told, the only difference has been that this application at home has been told that the server is at this host port A. Normally you have the server at let's say for us it is mail.boostel.edu port, I forget the port number. What is the port number for SMTP? Some port number, right? Instead of that, we say that no, it's right here on this host, and the port number is this. So that's the only thing that so the server, you can just program your application to send all the requests to port A. Now TCP doesn't do anything special. Anything that comes to port A, it just delivers to port A. And on this side, you don't tell anything to the server. Are we done?